In this video, we'll review the BJT voltage current characteristics. On this slide, we see the NPN and PNP type BJTs along with their schematic symbols. First, you'll note that the base terminal in the schematic symbol is connected to the conducting portion of the channel. That's because in the BJT, unlike the MOSFET, the base is physically connected to the conducting path of current between emitter and collector, whereas in a MOSFET, the gate region is separated from the conducting channel by an insulating oxide layer. The second point to note here is that the arrowhead always appears on the emitter terminal, both in the NPN and the PNP. And third, you'll note that the arrowhead always points in the direction of current flow when the device is in active mode. So, for an NPN transistor, when in active mode, positive current flows from collector to emitter because electrons are flowing the other way. On the other hand, in the PNP transistor, when in active mode, current's flowing in the emitter and out the collector, because that's the direction of whole carrier flow. The arrowhead not only reminds us of the direction of current flow, it's also a subtle reminder of the polarity of the PN junction formed between emitter and base. You'll see that that's another reason why the arrowhead changes direction between the NPN and PNP transistor types. Here we see a review and summary of the BJT modes of operation, along with the schematic symbol identifying the voltage levels corresponding to the different operating modes. The first operating mode is trivial, when the emitter base junction is reverse biased and the collector base junction is reverse biased. No current flows anywhere through the BJT other than some small leakage currents. We call this mode cutoff, or simply say the transistor is off for short. The second mode of operation we talked about is active mode operation. In this mode, the emitter base junction is forward biased. So that requires a forward voltage drop in the NPN transistor from base to emitter of approximately 0.7 volts for a silicon BJT. Also in active mode, we require a reverse bias for the collector base junction, or at least, let's say, a neutral bias. That is, we cannot have a strong forward bias between base and collector and still be in active mode. So we found that the transistor remains in active mode as long as a forward voltage drop of no more than 0.4 volts is applied between base and collector. So you see in normal active mode, the collector would be at a higher voltage than the base, but it can drop all the way down to as low as about 0.4 volts below the base and still be in active mode. However, if the collector drops further below that, 0.5, 0.6, 0.7 volts below the base, then the transistor is said to be in saturation mode. In saturation mode, the ratio of base and collector currents is no longer given by beta. It becomes less than that. These then are the three main modes of operation for the BJT. Now you might think about completing this table simply by considering the operating mode where the emitter base junction is reverse bias and the collector base junction is forward bias. In such an operating mode, you might expect it to operate in the exact opposite direction as active mode, where the collector is injecting excess electrons into the base, and these are being swept across the emitter. This can in fact happen, but remember that unlike a MOSFET, a BJT is not physically symmetric. The emitter is designed to have a much stronger carrier concentration than the base to ensure that its majority carriers far outweigh the majority carriers injected from the base into the emitter. And that's what helps ensure that the base current is only a very small fraction of the emitter current. The same is not true when it comes to the base collector junction. In fact, the collector junction is also often relatively weakly doped. And this is done in order to allow it to have a relatively high breakdown voltage in some cases. Nevertheless, the point is the emitter is particularly heavily doped, and so the device is asymmetric. When operated in this reverse active mode, the transistor therefore has a much lower value of beta, a much lower current gain between base current and emitter current. So it's unusual, although possible, to operate it in this mode. Here we have a similar picture for the PNP type BJT. Again, in order to ensure that the transistor is not in cutoff, we apply a forward bias across the emitter base junction. But in the case of the PNP transistor, that means the base has to be around 0.7 volts below the emitter. With that forward bias applied for active mode operation, the collector base junction should also be reverse biased, which implies the collector would be at an even lower voltage. However, it remains in active mode even if the collector voltage rises slightly above that of the base, until the point where the collector is, say, around 0.4 volts above the base. At that point in time, the current due to the forward bias base collector junction becomes significant, and the transistor is said to operate in saturation mode. So a key point is we need to maintain about 0.3 volts between emitter and collector in order to ensure the device remains in active mode. Again, reverse active mode is possible, though not recommended. Here we see the NPN schematic symbol shown with appropriate biasing to operate the transistor in active mode. VBE applies a forward bias between the base emitter across the base emitter junction, and VCB maintains a reverse bias across the collector base junction. Operating in active mode like this, the transistor is governed by these voltage current relationships. So the collector current is related to the base emitter voltage by this exponential relationship. That, remember, is the key property of a transistor. Current between two terminals is regulated by the voltage on another terminal. The base current is a very small fraction of that. It's the collector current divided by this current gain factor beta, where beta is typically in the range of 50 to 200. The emitter current is the carries all the collector current plus the base current in active mode. Alpha is another way of expressing the current gain. It's the fraction of emitter current that's carried by the collector. So it's a value very, very close to 1. For example, for a beta of 100, alpha would be approximately 0.99. Here we have a whole host of other useful relationships between the terminal currents of the BJT. We can typically relate the current at any two terminals of the BJT in active mode using either alpha or beta, where alpha and beta are related as shown here. You'll see here, for example, that with a large value of beta, alpha is a value slightly less than, but very close to 1. Finally, just a reminder that in these exponential relationships, Vt is the thermal voltage. It's proportional to absolute temperature, equal to Kt over Q, where K is Boltzmann's constant and Q is the fundamental electronic charge. It's always good to keep in mind, as a rule of thumb, that Vt is about 25 millivolts at room temperature. It's a nice round number. Here we see a similar picture for the PNP type transistor. So you'll note that to keep it in active mode, the base has to be at a lower voltage than the emitter, again about 0.7 volts to forward bias that junction. And the collector has to be at an even lower voltage to ensure a healthy reverse bias there. You'll notice in these voltage current expressions, not much changes except that the polarity of the base emitter voltage has to be reversed here. In these expressions, for the PNP transistor, we would replace VBE with VEB. Also, you'll note that the polarity of the currents is reversed compared to the NPN type transistor, with emitter current flowing into the emitter and collector current flowing out of the collector when in active mode. Also, current flows out of the base for the PNP transistor when in active mode. But keeping in mind these reversals in polarity, the exact same relationships hold. So here, imagine conducting a thought experiment where VCB, the reverse bias in an NPN transistor, is kept large so that that junction is reverse biased throughout this entire experiment. And imagine that we sweep VBE and measure the resulting collector current as we go along. Now we know that the collector current in this case is governed by this exponential relationship. So for small values of VBE, there's hardly any current flowing, and the transistor is said to be in cutoff. Once we get to forward voltages of, let's say, 0.6 and beyond, the transistor enters active mode and the collector current increases rapidly. Now a key point here is that VT is the thermal voltage proportional to absolute temperature. So therefore, when the temperature increases, VT will increase, and considering this expression here, current will decrease. So the result of the plots shown over here on the right, where we see for T1 greater than T2 greater than T3, that is, as we increase temperature, the exponential relationship shifts to the left. This is a key point because if you imagine the bias voltage being kept constant, I'm not even able to draw a straight line there and illustrate the point because the voltage current relationships are so steep there. But imagine keeping the bias voltages roughly constant, and as the circuit is activated, some current starts to flow, and that current flowing across a voltage drop through the BJT will result in some heat dissipation. The heat dissipation in turn elevates the temperature of the BJT. The elevated temperature, however, causes this voltage current relationship to shift to the left, which then causes the current to increase. Now the power dissipation is larger and more heating occurs, and the temperature continues to increase, the relationship continues to slide to the left, current increases, and you get this positive feedback effect that can cause what's called thermal runaway. That is, the temperature of the BJT continues to increase indefinitely until it overheats and gets damaged. This is something that doesn't occur in MOSFETs, where temperature increases when the transistor is in saturation mode actually cause the current to decrease. So extra care needs to be taken in BJT circuits to prevent this kind of thermal runaway, especially in circuits that are intended to deliver large amounts of power, large amounts of current to loads. Next, we need to augment our model of the BJT to account for an important effect, the so-called early effect. Until now, we've assumed that as long as the BJT is in active mode, the collector current remains practically independent of the collector voltage. As long as a reverse bias was maintained across the collector-base junction, we assumed that the collector current was just equal to beta times the base current and equal to alpha times the emitter current. However, this is not quite the case. There is some weak dependence of collector current on collector base voltage. And the reason stems from this relationship here. You may recall that the emitter current and collector current depend on the scale current, which is in turn inversely proportional to the width of the base region. We labeled that the effective width of the base region for a reason, because it's actually the space between depletion regions in the base. That's the width across which electrons in an NPN transistor must diffuse. And that diffusion arises because of a gradient in carrier concentration, minority carrier concentration in the p-type base. And of course, that gradient is set up because of a excess of minority electrons injected from the emitter in active mode. Now, since the rate of diffusion and therefore the current density flowing through the base is proportional to that gradient, we saw that it was inversely proportional to the effective base width. If the base gets narrower, then the gradient will increase and we'll see more current. Now, the effective width of the depletion region in turn does depend on, the effective base width W does in turn depend on the width of this collector base depletion region. It in turn depends on the amount of reverse bias applied. As we increase the reverse bias applied between collector and base, we will see the width of this depletion region increase, and therefore the width of the effective width of the base region will decrease. So the voltage between collector and base goes up, this depletion region width goes up, and therefore the effective base region width comes down, and that in turn, through this term here, will cause the collector current to ultimately increase. This is called the early effect. It should be noted that the effect is mild compared to the impact of base emitter bias voltage on collector current. However, it's still present and needs to be taken into account. Here we illustrate the impact of the early effect on the BJT's IV relationships. We're plotting here, for each plot, a sweep where collector current is being measured with VBE held fixed in each line, and the collector emitter voltage varied. Now we saw that as long as the collector emitter voltage is around 0.3 volts or higher, that we should be in active mode. Until now, we've assumed that in active mode, the collector current remained constant with respect to the collector voltage. So for different base emitter voltages, we would see more or less collector current, but that it wouldn't depend on the applied collector emitter voltage, as long as it was large enough to maintain a reverse bias across the collector base junction. But now we know that because of the early effect, there is some increase in collector current as the collector voltage increases, because that again widens the depletion region and thereby narrows the effective base width. So VCE increases, we get an increase in collector current. In fact, the early effect arises in such a way that if we make this IV plot for different values of VBE, obviously VBE is increasing as we go up from one line to another, and we look at the slope of the IV characteristics in active mode, they can be extrapolated to the left all the way back to the negative real axis here. And in fact, the early effect arises in such a way that they would all intersect at the exact same voltage. The voltage where they would intersect, hypothetically here, is therefore a useful parameter that allows us to quantify the slope of the IV characteristics in active mode for any value of VBE and any value of emitter and collector current. We will later consider this variation in collector current with collector emitter voltage to be a sort of a resistance, a small signal resistance. whose value is inversely proportional to the slope in this region. Again, just a reminder, these small signal quantities are just models. There's no physical resistance in the device itself. We just call it a resistance because it models a linear IV relationship, which we observe here in active mode.